Hi, I'm Alex Krentsel from UC Berkeley, and in this talk, I'm going to present our system, Turbo, that does real-time utility-aware bandwidth allocation to enable self-driving cars to use the cloud. Now, we started this work from the observation that there was a persistent and widening gap between the compute available at the edge on self-driving cars and in the cloud. State-of-the-art GPU performance has grown exponentially over recent years. But these new chips also come with serious infrastructure requirements. At the same time, cars have constraints that severely limit the compute that can run on them, including energy, stability, cooling, space, and perhaps most importantly, cost. An H100 chip costs about the same as an entire Tesla, which offers self-driving today. So taken together practically, the state-of-the-art GPUs available on the market today offer over an order of magnitude more compute, more flops, versus the best on-car GPUs available today. The trouble here is that ML progress has largely turned to model scaling in recent years to drive further performance gains. And these larger models do better, but they require more compute and memory to be able to run. Now, it's common for ML researchers to release multiple versions of their state-of-the-art models alongside the flagship model of different sizes. And here we take the efficient detector family of object detection models as an example, which have model sizes ranging from ED0 at the smallest up to ED7 as their flagship model. And benchmarking their runtimes on the best available on-car GPUs, compared to an H100 in the cloud, we find a very large runtime gap that quickly grows beyond reasonable runtime targets for on-car models. So as a result, only the smallest two of this family of models, ED0 and ED1, can run successfully within a target SLO. And this matters because these restrictions translate directly to decreased system performance. So here we see a frame captured by a Waymo vehicle from a front-facing camera. And zooming in on this frame, we can see that there's 4 cars there, 2 closer, 2 further away, and a pedestrian on the right. When we run this image through the actual ED models, we see that ED1 only detects those 2 vehicles on the left, misses the 2 vehicles in the back, and more importantly, misses the pedestrian on the right, who slightly blends into the background. Whereas ED7, the largest of the models, detects 3 of the 4 cars, and importantly, detects the pedestrian. So what can we do about this? Well, for some important context on the bigger picture, I'll go over the structure of these autonomous vehicle control planes today. AVs collect many gigabits per second of data, typically having a dozen plus cameras, a handful of LiDAR sensors, GPS, microphones, etc. And this data is then fed through a number of stages, starting from perception and localization, where we figure out what the objects in the scene are and where they are. Then to prediction, where we predict how those actors are going to move. Planning, where the car is going to decide its own trajectory in space. And control, where it actuates that trajectory. Now, in order to operate safely, the car must react within a very limited real-time SLO, roughly matching human performance and human reaction times on the order of a third of a second to a second. And then zooming into one of these stages, here the perception stage, we can see that the control pipeline is implemented as a compound AI system. It's a DAG of services, like these object detection services that run on each stream of the camera feeds, and run in parallel, producing bounding boxes that are then passed forward onto and through environment fusion and prediction. And while the exact latency targets are kind of proprietary and kept hidden by the companies, prior work estimates the SLOs for this object detection to be somewhere around 150 milliseconds. Now, coming back to our original problem, let's look at the simplified AV control plane with this diagram in the bottom right. This car has two cameras, and for the control plane, we're going to focus on just the 2 object detection services for these 2 cameras. omitting the later stages. Our original problem was that only these small models, ED1, are able to run on the on-card GPU within the target SLO of 150 milliseconds. Now, a natural solution might be to turn to the cloud. And the cloud does offer us access to as many powerful GPUs as we need, but there's a crucial challenge, which is to get there, we have to traverse cellular networks. And these networks have high ping latencies, very limited and variable bandwidth, and can be highly unreliable, which leads to missed deadlines and safety risks. And simply the volume of data alone collected by the car makes it infeasible to just move the control plane entirely to the cloud. To solve this problem, we consider selectively offloading a subset of the services that can make it to the cloud in time, which is effectively pooling together our bandwidth for some specific services to get a chance to go and use cloud resources. Now we observe that for any single service, the end-to-end runtime of offloading to the cloud is the current ping latency plus the propagation latency, or the time it takes to put the inputs onto the wire, plus the runtime of the model in the cloud. And looking at typical 5G cellular conditions reported in past measurement papers, and benchmarks that we ran ourselves on how long these models take to run in the cloud, we actually see that it becomes feasible to do so, to take some particular models and make it to the cloud and back in time. But in order to do this, we have to configure our selections very intentionally. We have control over the models that we choose to run and control over the way that we allocate bandwidth to a service and which service we give more bandwidth to. This raises the key question that our work addresses, which is we have to decide which services we're going to offload and which models we're going to choose for them to be able to run in the cloud. Allocating bandwidth to a service translates to giving it more cloud runtime budget, which allows it to run a larger, more accurate model. Now, there's many different possibilities. We could, in this case, in this example, share the bandwidth equally, and perhaps that enables both of our services here to step up to ED4. Or we might share the bandwidth unequally, and perhaps give camera 1 more bandwidth, thus allowing it to reach the cloud faster and run a larger model. Or maybe we even give camera 1 all of the bandwidth so that it can run the largest model, ED7, and leave camera 2 having its model running on the car, ED1. So the intuition is for how we should decide this is that different services might benefit different amounts from getting to run on these cloud models. So the approach that we take in our work of solving this problem is to extend the idea of utility curves to encode these trade-offs and benefit, and then to use that to do our bandwidth allocation and model selection. So more concretely, we start off offline by benchmarking each model's performance for each service using data that was collected prior. In our paper, we use the Waymo open data set for this benchmarking, with the benchmark being mean average precision, which is standard in the object detection literature. And I'll note here, we collect both the runtime and the accuracy experienced by that service for that model. And then next, we construct a utility curve for each model of that service independently. And this curve captures the benefit to the car, namely accuracy, for a given bandwidth allocation. And I'll note, you can see here, this ends up being a single step function, because if not given enough bandwidth, that model simply can't finish running in time to return a result. So it provides no benefit to the car. And as soon as you cross the threshold of there being enough bandwidth given to leave enough time to run, then the model provides some amount of bandwidth, namely its accuracy, some amount of utility, namely its accuracy. And then we aggregate these utility curves into a separate, into a complete service level aggregate curve, which captures the benefit to that service of allocating additional units of bandwidth. Now, finally, at runtime, we will jointly allocate bandwidth and select our cloud models according to what maximizes the average service utility across all of these services, which we formulate as an ILP that gets solved. I'll note then also that to maintain safety, for the case where the car gets disconnected or network conditions suddenly change, we always run the on-car model as fallback, and we opportunistically use the cloud results that are returned. Okay, so in the paper, we go into much more detail about the tricks needed to make this work. One problem we ran into is that naive model options simply require too much bandwidth to be practical with one service, let alone multiple, which resulted in virtually no benefit below 170 megabits per second. There's a bunch of tricks we use to help with this, including adding compression as an option, which adds local runtime and lowers accuracy on the cloud, but saves bandwidth, and allowing the option to run preprocessing on the car, which saves some bandwidth but adds local compute time. So we can see as a result, our final utility curves had many more step-up points at much lower bandwidths, effectively pulling kind of the curves to the left, adding more benefit at lower bandwidths. Now, in order to evaluate Turbo, we applied this method for deriving service utility curves for the efficient detector family of models on the open source Waymo data. And we implemented our ILP formulation of our optimization problem in Python and built out the Turbo control module and the Turbo client and server in both Python and Rust. And we ran our evaluation both in simulation, using pre-recorded data from Waymo, and in a real-world deployment, testing on a modified real car. Now, for our simulations, we ran them on this Waymo collected data set of 100,000 scenes of 20 seconds each, which provided 5 cameras, their video streams, with ground truth labels annotated by humans. And we constructed our control system to comprise 5 detection services and 1 planning service. And what we found as we swept the space of 5G cellular network conditions reported in prior works was that Turbo improves the average accuracy by up to a full 15.6 percentage points. And looking in the range of kind of very typical 5G conditions, a full 10 percentage points or more. In the paper, we break this down further to show the factor analysis of which components of our design contribute to this result. I want to note that this is a great result because in the ML literature, even increasing accuracy by a few percentage points becomes a big result and makes for a new state-of-the-art model. Then to evaluate Turbo's practical real-world benefits, we ran an actual shadow deployment of Turbo. We outfit a real car with 3 cameras, a local server, a 5G hotspot, an antenna, and reserved and had a Google Cloud server and GPU running in a data center. And we conducted some test drives in Sunnyvale, running Turbo over a period of 2 hours of driving on the highways and on neighborhood roads. I'll note for safety reasons, we didn't allow Turbo's control plane to feed to any of the car controls, but we did take all of the live incoming data and processed it, either on car or in the cloud. And our results found that Turbo very effectively enforced bandwidth allocations under these changing network conditions and selected the right amounts of bandwidth to allocate to each service in a way that maximized the average model accuracy boost. And we saw that the actual model accuracy boost experienced closely matched the expected accuracy boost that Turbo expected by its allocations. In the paper, we further report performance micro benchmarks that we recorded during our drive, showing the performance of our system. Now, we discuss many additional details in the paper that I don't have time to talk about now, including Turbo's economic feasibility, the benefit of deriving these utility curves dynamically and techniques for doing so, system micro benchmarks, and more. I encourage you to see the paper for those. But in closing, we've seen that the cloud edge GPU performance gap is just continuing to grow, and that cellular networks are a very real challenge for edge systems to try to use the cloud. And in this work, we presented Turbo, which is our system for real-time utility-aware bandwidth allocation that enables AVs to use the cloud. And it does this in a way that maintains safety, opportunistically maximizes performance, while minimizing the cost of network and cloud use. With that, thanks for your time, and I'll be happy to take any questions over email. You can reach me at akrentsel@berkeley.edu. Thanks.